We're using Sklearn's Gaussian process regressor, a powerful tool for regression tasks, and focusing on the DotProduct kernel, a specific way to calculate similarity between data points. I'll explain how the DotProduct kernel works and what its properties mean. The DotProduct kernel loves data centered around 0. It's super sensitive to where the data's average point is, its center. The kernel's behavior changes dramatically if you shift your data. The DotProduct kernel computes the dot product, which is like measuring how much two vectors point in the same direction. If you stretch or shrink the features, this changes the dot product significantly, affecting results. You must scale your features carefully when using the DotProduct kernel. The DotProduct kernel is essentially a linear kernel. It assumes that the relationship between your features and your target is a straight line. It's great for finding linear patterns, but might struggle with more complicated curves. I wouldn't recommend the DotProduct kernel for situations where you have many more features than data points. It's vulnerable to the curse of dimensionality. Performance suffers drastically in these high-dimensional spaces. Other kernels are better for such scenarios. This is just reminding you to choose all the options that are true about the DotProduct kernel. I calculate the DotProduct kernel by multiplying corresponding elements of two feature vectors, x, and then summing the results. This gives me a single number representing the similarity between the two data points based on their features. Think of it like this: the more similar the features, the higher the dot product. I'm designed to specifically find linear relationships. If the relationship between your features is a straight line, I shine. If not, my performance will be diminished. The average of my data significantly affects my results. Ideally, my data should be centered around 0, meaning the average of each feature is 0. If the average isn't 0, my calculations can be way off. I'm very sensitive to how much my features vary. If one feature is much larger than another, the larger one will dominate my results, possibly hiding the true relationship between features. So, consistent scaling of features is essential. In very high-dimensional spaces, things get tricky. My performance can degrade if I have too many features compared to the number of data points. This is related to the curse of dimensionality. I'm using Sklearn's gaussianprocessor with the DotProduct kernel to build a model. Think of it as a fancy tool for finding patterns in data. I'm facing a multiple-choice question that tests my understanding of this DotProduct kernel. This question wants me to identify the true characteristics of the DotProduct kernel. I need to carefully consider each statement. This statement is saying that the DotProduct kernel works best when the average of my data is 0, around the origin. I should remember this. This means that if I change the scale of my data, e.g., make my features bigger or smaller, this will drastically change the results of the DotProduct kernel. Therefore, I have to be careful and scale my features uniformly. The DotProduct kernel is good at finding linear relationships between features. When one feature changes, another changes proportionally. This statement says that the DotProduct kernel is great for high-dimensional data. This is usually wrong because many issues will happen. It's better to use a different kernel for such scenarios. The core of the DotProduct kernel is calculating the dot product of two vectors. It's basically multiplying corresponding elements and then summing up the results. Think of it as measuring the similarity between data points based on their feature values. The kernel's output tells me how similar two data points are. A larger output means higher similarity, based on the dot product. I'm using Sklearn's Gaussian process regressor, a powerful tool for regression tasks, specifically with the DotProduct kernel. This kernel is a crucial part of how the model learns relationships in the data. This is a multiple-choice question designed to test your understanding of the DotProduct kernel's properties. I'm asking you to identify which statements accurately describe the DotProduct kernel. This tests your knowledge of its strengths and limitations. This statement checks if you understand that the DotProduct kernel excels at capturing linear relationships between features in your data. This tests if you recognize that the DotProduct kernel's performance is greatly influenced by the mean of your data. Ideally, the data should be centered around 0. I'm testing whether you know that changes to the scale of your features directly affect the outcome of the dot product calculation, hence significantly impacting the kernel and therefore your model. This explores if you are aware of potential pitfalls when using the dot product kernel with high-dimensional data. There are challenges here related to the curse of dimensionality. The overall question format is a multiple-choice quiz focusing on your conceptual understanding of the dot product kernel. I see that statement A is correct. The dot product kernel uses the dot product of feature vectors. The dot product is a mathematical operation that directly measures the linear relationship between those vectors. So, it's perfect for when you expect the relationship between features to be linear. Think of it like this. If your data points are best explained by a straight line, then this kernel is your best friend. Absolutely, B is also right. The dot product kernel is really sensitive to where the data's center point is. The origin is the point, 0, 0, 0. And it is crucial that you have a mean of 0 for your data for the kernel to work correctly. Otherwise, it gives you wrong answers. You got it. C is another correct statement. The dot product kernel's calculations are directly affected by the size of your feature values. If you change your scaling, the kernel's outcome changes. This means you have to be careful with how you scale your data to avoid problems. I disagree with statement D. When you have many more features than data points, it's called the curse of dimensionality. With that, using the dot product kernel can be problematic and lead to overfitting. You'll want to consider other kernels more appropriate for higher dimensions. See the dot product kernel as a way to measure how similar two things are by multiplying their corresponding features and adding up the results. Think of it like comparing shopping lists. The more items you have in common and in similar quantities, the higher the dot product, and the more similar your lists are. The dot product kernel thrives when the relationship between the features is straightforwardly linear. That's because it directly reflects how changes in one feature relate proportionally to changes in the other. Think of a simple line on a graph. A higher dot product means the points sit closer to that line. I've found that the dot product kernel is very sensitive to the scale of your features. If you change how big or small your numbers are, it heavily affects the outcome. Imagine measuring distances in centimeters versus kilometers. It changes the numbers dramatically, and thus, the outcome. Using the dot product kernel with tons of features compared to data points is typically a bad idea. It's like trying to find a needle in a massive haystack in a pitch-black room. It's hard to get reliable results and you end up with a model that might not generalize well. You'll likely need other, more appropriate kernels. I see this as the overall structure of how the dot product kernel works. It takes in feature vectors, computes their dot product, and outputs a similarity score. Think of it as a blueprint for calculating how similar two data points are based on their features. These are the input data points. Each is represented as a vector of features. For example, X could be 1, 2, 3, representing 3 features for one data point, and X could be 4, 5, 6, representing the same 3 features for a different data point. We use these vectors to compute similarity. This is the core of the dot product kernel. It says that the similarity, k, x, x, between two feature vectors, x and x, is calculated by taking their dot product. The dot product is found by multiplying corresponding elements in the two vectors and then adding them up. 1 asterisk 4 plus 2 asterisk 5 plus 3 asterisk 6 equals 32 in my example. A larger dot product suggests greater similarity. The result of the dot product calculation is a single number that represents the similarity between the two input data points. The higher this number, the more similar the data points are according to this kernel. It's like a similarity score. This statement is true because the dot product itself captures linear relationships between features. If your data shows a mostly linear relationship, this kernel is a good choice. This is also true. The dot product is heavily influenced by the mean of your data. Ideally, data should be centered around 0, the origin, for the dot product kernel to work best. This statement is true. The magnitude of the dot product changes dramatically if you change the scale of your features. Consequently, the kernel output and model performance will change. You need to pay attention to feature scaling. This is false. The DotProduct kernel struggles with high-dimensional data because of the curse of dimensionality. In this situation, other kernels may be much more suitable. This refers to using a Gaussian process regressor model with a DotProduct kernel to predict continuous values. Gaussian processes are probabilistic models. The DotProduct kernel gives the model its specific assumptions about relationships between features.